All right, so today we're going to start a new topic. This is, I don't want to worry anybody, but historically, this is one of the more confusing topics that we're going to talk about. It's also one of the more important ones. So I'm going to do my best to try to explain this. As always, I'm going to kind of start more on the sort of theoretical, conceptual side, and then we will finish up probably in a few lectures with just a number of examples of how do we apply some of these concepts to a particular problem. All right, so we're going to start with sort of revisiting this definition of stress at a point. And one of the things that I want to stress is the coordinate system here, right? So this is for a XY coordinate system. It looks like that, right? And if we take a look at how we define our sigmas, sigma ij, let's say, the I portion of that is the direction of the area. Right? And the j portion of that is the direction of the force. Right? So we define stress. It has two directions associated with it. It has the direction that the force is acting, and then it has the direction of the area that the force is acting on, right? So it's sigma ij. One thing to note, that tau xy equals sigma xy, right? So this guy here, this is just different nomenclature. So I don't want you to get confused. Your book uses tau xy. In the future, I promise, at some point, you will also see it written as sigma xy. Just know that they are the same thing. And the last thing I've got to point out here, sort of for completeness, is that these dimensions of this cube are dx here and dy here, right? So it's this infinitesimal cube, right? And these are all the positive stresses that can act on it. So if we look at, for example, sigma xx, that is acting on a positive x face, right? Because and I should sort of put here perpendicular. So because the normal of that face is going in the positive x direction, right? And then you look at the arrow is also going in the positive x direction, so that has a positive area and a positive force direction. It is a positive stress. Okay? That if we come over here and we look at this sigma xx, right? This guy is on a negative x face because, again, the normal now is pointing in the negative x direction, and the arrow is, the force direction is also in the negative x direction. So that's a negative area and a negative force. That makes it a positive stress again, and that's why it's plotted here. Everything that you see here is a positive sign convention, right? So tau xy, if we just do one of those, right? So this guy here, right? That is a positive tau xy. Okay, so why is that? Well, it is on a positive x face, and the stress, the arrow, is going in the positive y direction. Right? Similarly, this guy here is on a positive y face, and the arrow is going in the positive x direction, right? So that x and y, or y and x, we showed previously that tau xy and tau yx are the same, right? And then if we come down, sort of keep going around this cube, this guy here, it's on a negative x face, and the arrow is pointing in the negative y direction. Negative and negative is a positive, right? And this guy here is on a negative y face, and the arrow is pointing in the negative x direction. So again, negative times a negative is a positive, right? So all of these guys, basically axial stresses, our tension is positive, right? Because the direction of the force and the direction of the arrow align with one another. So it's pulling away from the area. And the tau xy's, it's just, if it's a positive area and the arrow is going in the positive direction, it's positive. If it's a negative arrow or a negative area and the arrow is going in the negative direction, it's also positive. So only when those things are mixed and matched, one positive, one negative, is that a negative stress. Okay, so what we're going to do on this lecture is to talk about stress transformation. So the question really is, I've defined this XY coordinate system, right? But in many ways that is completely arbitrary, right? We're always saying, X is to the right and Y is up, okay? But that depends completely on your perspective, right? If I walk around behind this cube and look back at it, sort of like I'm behind the blackboard looking out at the class, right? Everything is flipped. The X coordinate system is flipped. Now X would be going to the left, right? So it's really completely arbitrary. You could say Y is always opposite the direction of gravity, if there's some sort of absolute there. But in reality, the XY coordinate system that we typically draw is in fact arbitrary, right? So I could draw it in a different direction, right? For example, what happens if I define my X and Y coordinate system like this, and I call them X prime, Y prime, right? So now I've rotated by some theta, right? Now what are the stresses? They're clearly not going to be sigma xx, sigma yy, and tau xy, right? I have now rotated my perspective, right? And that is going to change both the area and the direction of these forces, right? So the areas are different in this new coordinate system, and the direction of the forces are different in this new coordinate system, right? So let's see how that sort of works out here. Okay, so let me rewrite this guy here, stress transformation, so we make sure we understand what we're doing. Okay. So if I draw a cube here, my stress cube again, and then I'm going to draw my positive stresses again. You should get very good at drawing these. We're going to draw them a lot. Okay. Then I can label them sigma xx, tau xy, and sigma yy. Right? So I'm going to stop short of labeling all of them. Just understand that they're always in the, if sigma xx is to the right, then sigma xx is also to the left, right? So there's really only 3 independent stresses that we have here. So I'm going to draw our standard coordinate system, right? So this is my X and Y coordinate system, okay? And then I'm going to draw a new coordinate system, and this one I guess I'll draw in green. And this new coordinate system I'm going to label X prime, Y prime. Okay? And then I'm going to take a cut in line with that coordinate system, right? So it'll look something like this. Let me try to draw it to scale. Right, so it's going to look something like that. So I've just taken this cut here. That is my theta, right? And now my y prime is along that cut, right? And my x prime is perpendicular to that cut. So it looks something like this. And what I'm going to try to do here is highlight what is staying. Right? So I'm getting rid of everything except this little triangle. Right? And now what I want to solve for are the stresses that are along this let me undo that and hit that guy. So my stress that's along there, right? And then perpendicular to there. So this guy will be called tau xy prime, and this guy will be called tau xx prime. Right? I'm sorry, it's sort of getting a little crowded in here, but that's sort of the concept, right? So this is what we're doing. We're saying, okay, we've defined the stress at a point in terms of our global coordinate system, capital X, capital Y, right? And then I'm rotating that coordinate system, right? And that coordinate system is rotated by a theta. So let me just draw that theta here, right? And that, by the way, is the same as that theta, right? So all of these are the same. So I've basically taken x and I've rotated it, in this case counterclockwise, by a specific theta, right? And now what I want to do is I want to solve for the stresses that are on that new face, that face that's oriented in this new theta direction, right? So let me come over to the right here, and the key is to solve for sigma xx prime and tau xy prime, right? So basically, what are the normal force and what are the shear force on this new plane, right? And in order to do that, we're going to use equilibrium. In the x prime and y prime directions. So these are the new coordinate system. So I'm going to sum forces along this x prime axis, right? And then I'm going to sum forces along this y prime axis, right? And equilibrium holds regardless of the coordinate system that you're defining, right? Okay, so now let me redraw this a little bit, and I'm going to draw it. I'm going to try to draw it a little bigger, and I'm going to also try to draw it roughly the same angle, right? That angle, by the way, is completely arbitrary, right? You can choose any angle, and this will still work, right? So that's my theta. Let me again highlight this so we make sure you understand what is sort of this material and what is not. Okay, and now we've got to draw these forces again, or stresses. So, did it again. So that guy is sigma xx prime. In fact, I did it a little. I'll really try to accentuate the perpendicular there. And then this guy is parallel, right? So this is my tau xy prime, and this is my sigma xx prime, right? And then we've got our old stresses, right? So this is, let's see, downward here. Oh. Downward here. This guy was in this direction, right? This guy was perpendicular away from that face, and this guy was perpendicular away from this face, right? So if we're going to, and let me do this, I'll call this guy black, and I'm going to say that this line here, right, that line there I'm going to call A1, right? Sorry, A2, I guess I have it in the notes. A2. And then this line here, I'll do it in red. Oh, I did it again. I'll do it in red. Right. And that line there, we're going to call A1. Right? So it turns out that we cannot, you don't do equilibrium in terms of stresses, you do them in terms of forces. And so the first thing that we've got to do here is define the areas on which these stresses are acting, right? So sigma xx here, right? So that's sigma xx. This is tau xy, and this is sigma yy, and this, of course, is also tau xy, like that. So sigma xx is acting on area 2, right? So if I multiply it by area 2, that's what I get is the total force going in the left direction, right? Going to the left. Tau xy is also acting on area 2. I need to leave myself a little bit more room here. So this is tau xy times area 2, right? Then this tau xy down here, I should also leave myself a little more room, didn't plan very well. This is tau xy times area 1, right? And this is sigma yy times area 1, right? All right. And then this guy here is actually sigma xx times A. That's the total, that's the area of the cut, right? And then this would be tau xy times A, just like that. So there's actually a couple things that we have to account for here. First, we've got to calculate the area, A1 and A2, in terms of this theta and the the area along the cut, right? What you can see, and I tried to accentuate this, is that the cut can happen at any angle. So you can see A1 is way smaller than A2. And both of them are smaller than capital A, right? So that geometry has to be accounted for. And so we're going to do that when we sum forces in the x prime and y prime direction. The second thing that has to happen is that all of these forces that you see have to be broken down into components along the x prime direction and along the y prime direction, right? Because if I'm going to sum forces along the y prime direction, that's where this tau xy prime comes in, right? It has no component along the x prime direction. It's running perpendicular to it. And when I sum forces along the x prime direction, then this sigma x prime comes into it, right? That has no component along the y prime direction. All right. So, what did I do here? Okay, sorry, I shut my notes down on accident. Okay, here we are. All right, so let's do, I guess I'll do it in black. We're going to sum forces. Sum forces in the x prime direction, and those have to equal 0. Right? So let's get going. This is going to be a little messy. I'm gonna warn you, but we will clean it up. And then after this lecture, I'm I'm going to show you of a more intuitive way of looking at the stress transformation equations. Right? The point here is that you understand where they're coming from. Right? So this is going to be sigma xx prime times A. Right? So that is going in the positive, this is the positive x prime direction, and that guy there is the positive y prime direction, right? So that's in the positive y prime direction. Then if we look at sigma xx, right? So this is sigma xx, that's the original coordinate system. Then its area is actually A times cosine theta, right? So how do I know that? Well, look at where theta is. Cosine is adjacent over hypotenuse, so that would be A2 divided by A, right? And if I multiply A2 divided by A, I just get A2, right? So A times cosine theta is the same as A2, right? So I can write this here. So that is A2, right? And then this is cosine theta, right? This is for the direction. Direction of force, right? So I correct first for the area, right? And then I correct again for the force, right? If that makes sense, right? So there's two cosines here, not just one. Let me put a parentheses around that whole thing, right? Then we can do minus tau xy. You can see it's moving downward, right? That's going to be, it's going to have a component in the minus sigma, or in the minus x prime direction, right? And this one, again, is going to have a cosine theta, right? And the reason it has a cosine theta is it's acting on the same area too, right? So it's going to be, in order to turn that into a force, I've got to multiply it by the same area, right? But now it's going in the opposite direction, right? Perpendicular, so I need to make it times sine theta. Right? So that is the force caused by tau xy acting in the x prime direction. And then we can continue with this, right? So this will be sigma yy. This will now be a sine theta, right? So that guy there is actually A1, right? And you can look, A1 would be opposite over, the sine of theta is opposite over hypotenuse, right? So that is, that will be A1 over A, and if I multiply that by A, I get A1, right? So same sort of thing that's happening. And then this guy is sine theta. That's again to pick up the direction of sigma yy in the x prime direction, right? And then finally, we've got a tau xy, and this is a sine theta. Again, this is A1, right? And then this is now, I've got to multiply it by cosine theta to pick up the component that is in the x prime direction, right? So this is for the direction of the force. And all of that equals 0. Okay. So hopefully what you can see here, I'm not going to write it, but you can see it in your book. Hopefully what you can see is that you can easily sum forces, right, in the y prime direction as well, right? And you're going to get a very similar expression, right? In fact, what you're going to get is all of the last terms, the cosine theta, sine theta, cosine theta, they're all going to flip. Because now we're looking at the perpendicular component, right? And that this component here is just going to be tau xy prime times a, right? So I'm going to get two equations, right? And I'm going to get two unknowns, right? And so we can solve for them. And what we're going to end up with, so I'm sort of waving my hands a little bit. If you want to see the derivation, it is in your book. You can also Google it. It's all over the place. What's important here are these final equations. So we can now, I guess I'll do it in blue again. Maybe I'll just write them that these are the final stress transformation equations. Right. And they are that sigma xx prime, like this, equals sigma xx plus sigma yy divided by 2. Right. And that is then plus a sigma xx minus sigma yy divided by 2 times a cosine 2 theta plus a tau xy times a sine 2 theta. Like that. In fact, you know what? Sorry about this. Let me rewrite that so they're not falling off the page. Because I know when people come back to look at this, they're going to want this a little bit neater. Plus sigma yy, that's going to be divided by 2. And this will be a plus sigma xx minus sigma yy, again, divided by 2, times a cosine 2 theta, right? And then this is a plus tau xy times a sine of 2 theta, right? So that's my sigma xx prime. Then if I want my sigma yy prime, right, everything is the same except this sign here, right, and this sign here. So they flip, right, but everything else will be the same. So this will be sigma xx plus sigma yy divided by 2. This will be a minus now, sigma xx minus sigma yy divided by 2. And this is still cosine 2 theta. And then this guy is now a minus tau, minus tau xy times sine 2 theta, just like that. And then this is the last one, which will be, we'll do it right here, tau xy prime. And then this is a little different, so this is a minus sigma xx, a minus sigma yy. Those are divided by 2. And then that is times a sine 2 theta, and then we add to that tau xy cosine 2 theta, just like that. So these are our equations, and I know what you're thinking. You're thinking, how is he going to expect us to solve problems with these stupid equations? And there are a couple things that are important here. One, that you understand where these equations come from, right? So these equations come from force equilibrium using the stresses on this infinitesimal sort of elements, right? So I start with our standard stress cube, and then I make a cut at a certain theta, right? And then I simply apply equilibrium. So I sum forces perpendicular to that cut, and then I sum forces parallel to that cut. And that gives me these expressions, right? I can also make a cut perpendicular to this, right? So it'll be theta plus 90 degrees, and that's how I can solve for my sigma yy prime, right? I'm not going to ask you to do it, right? But it is important that you understand where these expressions come from, right? So that's the number one thing, and that's really what's important here, because as we move forward conceptually, you've got to understand when I talk about transforming stresses to a different coordinate system, you have to understand what that means, right? That I'm actually sort of rotating the cube, and as I rotate this cube, the magnitude of the stresses change, right? And it's not just sine theta or cosine theta. It's both the area is changing that the stress is acting on, and the direction of the force that is the component of the stress, right? So it's a little bit more complex than that. And so we end up with these stress transformation equations. Now, as long as you have a calculator, right, you can plug in and, use these expressions, right? The only thing that you probably, that might jump out at you as a little strange is all of these two thetas that are within the those trigonometric functions. So the sines and the cosines are not sine theta or cosine theta. They're actually sine 2 theta and cosine 2 theta. I wouldn't get too confused about that. Basically, what we're doing is we're using identities. So I'm using identities for this cosine theta times sine theta, right? So all of a sudden that becomes cosine 2 theta and so forth, right? So it's just a simplification. The point here is, so if you've got, 45 degrees is your theta, then 2 theta would be 90 degrees, and then the cosine of 90 degrees is what you would dump in there, right? So the mechanics of actually calculating sine 2 theta or cosine 2 theta should be quite simple, right? I understand conceptually it's not, it doesn't probably make a lot of sense to you right now, but it just comes from that identity, and it's a means of simplification, right? And so next time, what we're going to do is look at these equations, and we're going to, I'm going to give you a more intuitive way of interpreting them. And so it turns out that these equations in sigma tau space actually define a circle, right? And they have a center of that circle, and they have a radius of that circle. And no matter how I'm transforming the stresses at any point in my material, they are going to follow this circle, right? And that circle is called Moore's circle. And if I do a decent job of explaining it, it is something that you guys will remember for a very long time, because it is quite intuitive, and it is, and because it's intuitive and graphical, it tends to be fairly easy to remember. Paradoxically, it's also quite challenging when you're first learning it.